Integrated rate law. These laws are basically equations that express the concentration of a reactant in a reaction as a function of time. So if we take the rate law that we have seen before in case of a reaction, so A, if let's say A is my reactant, rate is equal to K multiplied by concentration of A to the power of X, M, N, whatever it is. So if we take this rate law and we integrate it over the period of time T, that gives us integrated rate law. So if we take first order kinetics, it gives us an integrated rate law that would look like this. Natural log of AT over A0 is equal to minus KT, and if we rearrange it, it basically would look something like this, which is natural log of AT. Here AT is the concentration of A at time T, when time T has passed, minus KTT, here is the amount of time that has passed. K is the rate constant, and A0 here is the concentration of A initially, meaning at time 0. And if you make a graph of natural log of A versus time, it would give us a linear plot, which would look something like that. And linear plot usually is represented by this equation, y is equal to mx plus b, which means if I write this equation as y equals mx plus b in this particular format, where x is my time, y is the natural log, so natural log which you see on the y-axis versus time which we see on the x-axis, then the slope is going to be negative kt, negative, and that's why this is going down, and the intercept b is going to be equal to log a0. So here's what the graphically first order kinetics would look like. So this is what the graph would look like. If we make a graph of ln AT over time, it would give us a straight line as long as we make a graph of ln AT over time, and the slope is going to be equal to minus k. Similarly, we can make this use this approach to integrate the rate law and get it for zero order kinetics. It would look something like this: AT is equal to minus KT plus A0, which means we would get a straight line for a graph of AT versus time. In case of a second order kinetics, the equation would look something like this. So if we want to rearrange it to give us a plot, straight line, linear plot, we need to make a graph of 1 over AT versus time, and our y-intercept now will be equal to 1 over A0, whereas our slope is going to be going up, it would be equal to k. So what you need to remember here in these equations is basically these equations will be provided to you. It will be mentioned that this is a zero order kinetics, this is the first order, and this is the second order kinetics. The questions would basically just provide you with enough information so that you can use one of these equations to find the missing information. For instance, AT will be given to you, A0 will be given to you, T will be given to you, and question will tell you it's a zero order kinetics. So figure out what is the rate constant in this equation. So in this case, because it says it's a zero order, this is the equation you apply. So you just have to know which equation and how to use the equation. For instance, let's try this question. The rate constant for a second order kinetic reaction is this. What is the original amount present if after 2 hours there's 0.35 molar available? So let's narrow down what the information that the question provides us. First thing, it's a second order reaction. This is the rate constant, which means this is the K given to us. What is the original amount? So if this is my reactant A, the question is asking what is original, so what is the value at time 0? If after 2 hours, which means that's how much time has passed, 0.25 is available. So this is how much is left after time T has passed. So these are the information given, and we know that for a second order kinetics, this is the integrated rate law. AT is given to us K is given to us, T is given to us. We just have to rearrange to solve for this. So 1 over A0 negative, which means I need to get rid of this. So if I want to isolate this, I need to get rid of 1 over AT. So I would, because this is in positive, I would add negative of this, which means I have to add negative of this here as well, will be KT minus 1 over AT. If I want to get rid of this negative sign, which means I would make this a plus, which would make this minus, and this would become plus. And because I'm interested in solving for this, I would have to finally rearrange this equation. So we just plug in all the values here. The important thing is K, the unit is molar inverse, second inverse, whereas time is given to us in hours. So first thing we'll have to do is we'll have to convert 2 hours into seconds so that the units match up, which would be 1 hour 60 minutes and then 1 minute 60 seconds. So minute, hour, hour gone, which gives you around 36, 7200 seconds. So we just plug all of this into this equation and we can solve for the missing information. The answer is 0.40 molar. That is how much was there in the beginning. The radioactive decay of a new atom occurs so that after 21 days, the original amount is reduced to 33%. What is the rate constant for the reaction? The question is asking what is K, T is the time given, and this is a radioactive decay. You need to remember radioactive decay is always first order kinetics. So in this case, it's talking about the concentration in percentage, which makes it a little bit easier. The question says the original amount is reduced to 33%. So that is how much is left after time t has passed. If I can assume that the original, because we are talking about percentage, the best is you assume that the maximum amount possible is 100 because that's the maximum percentage. So if I assume A0 is 100, that means I can say AT is 33% of 100, which is 33. So if we use directly these numbers, we can solve for K. The equation for this order is right here. Again, you do not have to memorize these. These will be provided to you in the formula sheet during exam. If this is the expression, A0 is 100, AT is 33, K is what we need to figure out, and time t is given to us as 21 days. So we just rearrange the equation again and we solve for the missing information. So integrated rate law is very straightforward. You just have to use the rate laws to solve for the missing information. For instance, another question, at 1000 degrees Celsius, cyclobutane decomposes in a first order kinetics with the high rate constant, which means K, to 2 molecules of ethylene. The initial C4H8 concentration is this. So this is the initial concentration, A0. What is the concentration after this much time has passed? So that's my T. And the question is asking to solve the concentration at time T. Okay, because this is a first order kinetics, we'll just use the first order rate law and plug everything into the expression and solve for the missing information. Remember, whenever we want to get rid of natural log, if natural log of x is equal to y, then we want to solve for x, we need to take e to the power of all of this on both the sides, which means x will be equal to e to the power of y. That is how natural log is removed. So if you're not comfortable with math, just remember this is the rule. If you want to get rid of natural log, we raise both the sides to the power of small e. And in your calculator, there should be a function of e so that you can use that. It's small e, not capital. Then there was a second part to this question, which was if 70% of C4H8 has decomposed, 30%, what would be the constant? So it's the same question now, but in percentage. 70% has decomposed, which means what's left at time t is going to be 30%, which means my A0 is 100. So if A is 100, then what's left is 30. Again, the amounts are given. We just have to plug the values into the expression. This is 100. This is what's left. This is given to us. We just have to figure out how long does it take. So we first figure out K using from part A, and then we plug it in to this expression. Half-life. We've talked about this in nuclear chemistry as well. Half-life is the amount of time that is needed to reduce the concentration of the reactant to half of its original value. So if I started with 100, the amount of time it takes for the sample to reduce to 50 is called as half-life, for it to turn into half of its original value. For example, next half-life would be when 50 turns 25, that's the second half-life. And in some cases, we can, in all the cases of different order of reaction, we can use the integrated rate law to calculate what is T half. So for instance, these are the equations for zero order. T half is equal to A0 over 2K. For first order, T half is equal to ln 2 over K, which is basically natural log of 2 is 0.693 divided by K. For a second order kinetics, it would follow this expression. Again, you do not have to memorize these will be provided to you. How were these obtained? If we use the expression, the integrated rate law that we saw before, and because we are talking about half-life, if I assume my A0 is 1 and AT is half of it, so that would be 0.5, plug all the values in the expression and we just solve for T half in terms of K. That is how we derive these equations. This is an overview of all the integrated rate law expressions that we saw. 0 for second order. So please remember to figure out what is integrated rate law and how can we use that rate law. This up until this part, all this information will be provided to you except for the units, and you just have to plug in the equations and use the right equation. One very easy way to remember which one is 0, which one's first and which one's second is in case of zero order, AT versus T will be a straight line. In case of first order, ln AT versus T will be a straight line. In second order, 1 over AT versus T will be the straight line. So if a graph is given to you and the question asks which rate law is this representing, which order, this is 0, this is first, and this is second order. For instance, for a first order reaction, what should be plotted in order to observe a linear relationship? It would always be natural log versus time. So that would be the answer for a first order. For a second order, it would be 1 over reactant versus time. Or for the zero order, it would be reactant versus time. So we just have to remember which equation is for what order. Now we'll just try a bunch of examples using the same concept. You can try them on your own and then come back and look at the answers. For the following first order reaction, the rate constant is this, which means this is K. What is the half-life? We will use the equation for half-life and the relationship between half-life and K for a first order kinetics and plug in the values and solve for the half-life. How long does it take for the concentration of cyclopropane to reach 1/4 of its initial value? So question is asking how long, meaning what's the time for a sample to become 1/4. So again, because this is relative, I can assume my A0 is 1, then my A at time t is going to be 1/4 of 1, which is 1/4. So we just use these numbers and the value of K given to us and we can solve for time it takes. Or because it's getting 1/4, if we think just in like for a minute, it would tell us how much time, once we figure out half-life from here, After 1 half-life, it becomes half. After 2 half-life, it will become 1/4 of the original. So 2 half-lives is equal to the answer for the amount of time it took here. But otherwise, you can also use the integrated rate law to solve for this. So half-life was calculated. Half-life was calculated based on this. T half is natural log of 2 divided by k. We got the half-life, and because it is 1/4, we will use twice the amount, so it would be this. Alternatively, you can use this equation as well, like I mentioned earlier, and solve for time it took. A first order reaction has a half-life of this, so that's first order. Half-life is this much. Calculate the rate constant. Again, we just use the expression. Determine the percentage of reactant remaining after 25 minutes. Add 2 to 5. So again, this is the time that has passed. Question is asking, determine the percentage. Percentage means percentage remaining. So that would be how much is left, which would be 80 divided by how much was it initial times 100. That is what percentage means, which means if I can get the ratio of 80 over A0, I can use that to find number B. I don't have to solve for 80 and A0 separately as long as I just have a ratio from here. So we will use that equation again to solve for K, and then we will plug all the values into this equation. Natural log, again, to get rid of natural log, we'll raise this to the power of e, and we'll raise the whole thing to the power of e. So e to the power of this gives 0.761, which means this times 100 is your percentage. So after 25 minutes, 76.1% of the reactant is still present. Similar question, a first order reaction has a half-life of 25 minutes. If the initial concentration of A is this, what is the concentration of B after 50 minutes? So T is given, A0 is given, we just have to solve for what is AT. Again, we'll use the first order kinetics to solve for it, and